Okay, listen up. I'm pulling you off your tickets for a minute because we need to talk. We have to talk about one of the most dangerous traps in all of distributed systems. And no, this isn't some theoretical thing from a textbook. This is the kind of bug that silently eats user data for breakfast and doesn't even bother to leave a log file. What we're going to cover right now could literally save your project, so pay attention.
All right, so you remember yesterday, right? Day 19, we talked about the gossip protocol. We've got this awesome leaderless system where all our servers are just constantly chatting, sharing updates, trying to figure out the state of the world without some central boss calling all the shots. It's fantastic. It's super resilient.
But this is where it gets really, really dangerous. What happens when a user's action hits server A and then just a millisecond later, another action from that same user hits server B? Now, both servers have a totally different version of reality. So which one is the truth? And this right here perfectly captures the problem. I want you to imagine our servers getting into a full-blown argument. Server A is holding up its data, this glowing receipt, and it's screaming, "This is the latest! I'm right!" But then server B, it's pulsing. It holds up its receipt and yells, "No way, mine is!" They are both 100% convinced they're right. How does the system even begin to decide? Now, the simple answer, the one everyone thinks of first, is, well, just check the timestamp. Whichever write happened last wins. Sounds logical, right? Wrong. Absolutely wrong. And here is the reality check I need you to burn into your brain forever. We cannot trust the clock on the wall. In the distributed system, time is a lie.
So, why is time so completely unreliable? Well, first off, physical server clocks, they're not perfect. They drift. One clock runs a tiny bit faster, another a tiny bit slower, and pretty soon they just don't agree. Now, you might be thinking, but wait, we have Network Time Protocol, NTP, to sync them. And yeah, we do, but NTP is not magic. It gets them close, but because of network lag, there's always a margin of error. It is completely possible for a packet to leave server A at timestamp 100 and arrive at server B when its clock says 99. The effect happens before the cause. Yeah, time travel is real in our systems, and it will absolutely destroy your data.
I mean, just look at this chaos. Imagine your one source of truth for time just glitching out. It jitters, it jumps around, it even runs backward for a second. That is exactly the level of trust you should put in a raw timestamp. 0. None. Okay, let's break this down, because this isn't a cartoon. This is a real-world data disaster. Look closely. Client A writes x equals 1 to node 1. The timestamp is 42.004. Okay, that replicates out. Then, client B reads that value and writes x equals 2 to node 3. Now, this clearly obviously happened after client A's write, but look at its timestamp, 42.003. Why? Because node 3's clock is just a little bit behind node 1's. So when node 2 gets both of these updates, it looks at the timestamps and says, well, 42.004 is newer than 42.003. And poof, it throws away the x equals 2 update. Client B's action is silently deleted. Gone. This whole strategy is called last write wins, or LWW, and it is an absolute footgun. Let me make this even more real for you. Let's walk through a little cautionary tale I like to call the shopping cart disaster. And trust me, this happens way more often than you'd think. So, it starts out simple enough. A user is on their phone, they find a brand new pair of shoes they love, and they add them to their shopping cart. That request flies across the internet, lands on server A. So far, so good. Everything's fine. But then, just 1 second later, the same user is on their iPad. They add a shirt to their cart, and thanks to our load balancing, that request hits a completely different machine, server B. And just like that, a race condition has officially begun. And now we have two realities. Server A is certain the cart contains shoes. Server B is just as certain the cart contains shirt. Neither server has any idea about the other item. So what's the truth? Well, the user expects their cart to have shoes, shirt, but that state doesn't actually exist anywhere in our entire database. And here's the plot twist. If we're using that naive last write wins strategy, the system is just going to look at those two totally unreliable timestamps, pick one as the winner, and declare it the one true cart. Which means the other item, it's just gone, silently deleted, no error message, no warning, nothing. The user comes back to check out, they only see the shirt, and they're just confused. I could have sworn added shoes. Maybe they add them again,
Or maybe they just get frustrated and leave. We just lost data, and we just lost a sale. This is the trap.
So how do we fix this? How do we build a system that is actually correct? Well, the answer is pretty radical. We take physical time and we throw it directly in the garbage. It's unreliable, it's a liar, and we are done using it to resolve our conflicts. We need a completely different way to understand the order of events.
And that brings us to the hero of our story, the vector clock. Now, a vector clock has absolutely nothing to do with the time of day. Instead, I want you to think of it like a set of counters. For every single piece of data, we just keep a list of which servers have modified it and a version number for each of those servers. It tracks causality, what happened because of what, not what time the clock on the wall happened to say. I want you to picture it just like this. Every piece of data in our system, every shopping cart, gets this little neon barcode stamped right onto it. This barcode is its version, its entire DNA history. So when ServerA touches it for the very first time, the stamp just reads ServerA 1. Simple enough. Now, let's trace this on the diagram. Let's go slow here, because this is important. Okay, first, step 1. A client writes data D1, and server SX handles it. The vector clock is super simple, SX1. Now find step 2. Another client updates that data to D2 on the exact same server, so the clock just increments. D2, SX2. This is easy. It's a simple linear history. But now, look what happens. The flow splits. Two different clients read D2. The first client updates it to D3 and writes it to server SY. See it on the diagram? Its history is now D3, SX2, SY1. See how it knows it came from version 2 of SX's data? At the exact same time, the other client updates D2 to D4 and writes to server SC. Its clock becomes D4, SX2, SZ1. We now have two conflicting children that both came from D2. Okay, and here is the most crucial part, step 5. A client tries to read the data, and the system gives it back both D3 and D4. The system sees those conflicting vector clocks and it flat out refuses to guess which one is right. So now, it's the client's job to look at both versions, merge them into a new correct version, we'll call it D5, and write that back. The new vector clock for D5 now includes the history from all three servers, D5, SX3, SY1, SC1. And just like that, we've resolved the conflict without losing a single piece of data.
So let's just restate that really critical question. When the database gets two different updates with conflicting vector clocks, what does it do? Does it flip a coin? Does it just pick one at random?
No. It does the only safe, the only correct thing possible. It keeps both of them. It doesn't throw anything away. It acknowledges that there's a conflict, and it saves both versions of the data. They are now officially known as siblings. They are two equally valid, concurrent states that just need to be reconciled.
And what does that mean for our user? It means all of that complexity gets pushed to the client application. So the next time the user opens their app, they don't see a mysteriously missing item. No. Instead, they might see a little pop-up like this. You have items in your cart from another device. Would you like to merge them? The application now has both versions of the cart, the shoes and the shirt, and it can present a single unified view to the user for them to confirm.
And this slide right here, this is the whole point. It's a separation of concerns. The database has one job, and one job only, preserve data. Never, ever, ever lose a write. The application's job is to handle the ambiguity, to resolve the conflicts, because only the application actually understands the business logic. Look, this isn't a bug. This is a core design feature of a robust, fault-tolerant system. You are trading what looks like simple automatic resolution for a little bit of complexity that guarantees correctness. It's the right trade-off every single time.
So we've done it. We've solved the problem. By throwing physical time out the window and using vector clocks to track causality, we can safely handle concurrent writes and never silently lose data. We have escaped the data loss trap. But all this talk about generating unique version numbers, it brings up another massive, massive problem. How in the world does a service like Twitter generate a unique, sortable ID for thousands of tweets every single second across thousands of machines without a central point of failure?
Tomorrow, on day 21, we're going to build the solution from the ground up. We are going to design Twitter Snowflake, one of the most elegant and influential distributed ID generation systems ever created. You do not want to miss this one. Hit subscribe, and I'll see you tomorrow.